Trigonometric identities and equations. So we've already seen some definitions about the 6 trig ratios, so let's just recall those. For instance, sine theta is y over r, cos theta is x over r, and tan theta is y over r, and we've got the reciprocals to those. In addition, we've got a circle of radius r and points x and y, so we've got a Pythagorean formula here that would look like x squared plus y squared would be r squared, or r would be the square root of the sum of the opposite two sides. With all of this information, we can start to look at some other identities, and an identity is a trigonometric expression that is always true. So we can start to build some of them. What I mean by that is this. Let me show you an example. It's always true that if you take sine and you multiply it by cosecant, you'll always get 1. And if you use the definitions, well, y over r and r over y, these are reciprocals of each other. The r's cancel, the y's cancel, and you get 1. So it turns out that sine theta times cosecant theta is always 1. It doesn't matter what the theta value is. And this is actually true for all reciprocals. That's basically the definition of a reciprocal. So there are 3 identities that we will be using that might seem a little bit obvious. We've kind of already used them. They're known as the reciprocal identities, so let's state those. And I'll put them in a box. They're important enough to know by memory, but the fact that sine and cosecant are reciprocals to each other gives us that cosecant is equal to 1 over sine, and vice versa, sine is equal to 1 over cosecant. And likewise, secant is defined as 1 over cosine, and cotangent is defined as 1 over the tangent. Those are known as the 3 reciprocal identities. And as I said before, an identity is always true for all values of theta. And as I just mentioned, the identities may be rearranged. For instance, the first one, cosecant theta equals 1 over sine theta, that is always true. And because it is always true, you can do mathematical things to it. For instance, I can multiply both sides by sine theta, and if I multiplied both sides by sine theta, I would get something that would look like sine theta times cosecant theta equals 1, which was what I was trying to show earlier. Let's take a look at a couple other identities. These are called the quotient identities. Again, important enough to put in a box because you need to know these, but the first one is tangent, and it is the same as sine theta over cosine theta. And cotangent, which is the reciprocal, would be the other way around as a fraction, so cosine theta over sine theta. And let's just prove that these are true. So let's start with tan theta. Well, tan theta is y over x, and I want to try and show you that that's the same as sine theta over cos theta, and sine theta was y over r, and cosine theta was x over r. And notice if you take the top of this fraction and you multiply it by r, and the bottom of the fraction you also multiply it by r, so just making an equivalent fraction, that you can cancel out the r's, and this gives you y over x. So it is actually true that tan theta from the definitions is equal to sine theta over cosine theta, and likewise with cotan theta. You don't have to know these proofs, they're helpful, but the identities you do have to know. The things that I put in the green boxes in these notes you absolutely must know. Let's take a look at the next type of identities. This is a little lead-in to what are called the Pythagorean identities. And so let's start off with a little bit of Pythagoras. And in that, I want to know if I take sine squared theta and I add cosine squared theta, what do I get? So I know this doesn't really look like Pythagoras, but I have something squared plus something else squared, so maybe it'll give me something squared, kind of like x squared plus y squared is equal to the hypotenuse squared, or a squared plus b squared equals c squared. So let's generate these definitions. Sine squared theta, and by the way, sine squared theta is just a shorthand way of writing sine theta squared, or sine theta times sine theta. That's just a little aside for you. The definition of sine is it's y over r, so sine squared is y over r squared. And cosine is x over r, so cosine squared is x over r squared. And using some exponent rules, I can get that this is y squared over r squared and x squared over r squared. And combining these together, I get y squared plus x squared all over r squared. Oh, wait a sec. We had a definition that x squared and y squared on that circle was equal to r squared. So that means this x squared plus y squared on the top can really be just r squared. And r squared divided by r squared is equal to 1. Therefore, sine squared theta and cosine squared theta should also be equal to 1. And that is one of the identities that we will be using quite a bit, and it's one of the 3 Pythagorean identities. So let's put that in a green box, and I'll show you what the other 2 are. Okay, so there's the first identity. Now, the way that we can generate 2 other identities is kind of sneaky. If I take this and I say, okay, it's always true, it's one of the identities, I can then start to manipulate it. And so I'm going to manipulate it in a very specific way, which is I'm going to take each term and I'm going to divide each term by sine squared. And by doing that, I generate a new formula. And so sine squared divided by sine squared is 1 plus cos squared over sine squared. Well, cos theta over sine theta is cotan. So cos squared over sine squared is cotan squared. And then 1 over sine squared, well, 1 over sine is cosecant. So 1 over sine squared is cosecant squared theta. And I've done just a small amount of work to generate another formula, but in terms of cotans and cosecants. Let's take a look at doing this another way that will generate our third Pythagorean identity by dividing by something different than sine squareds. So this time, instead, I'm going to divide everything by cos squareds. So let's take a look and see what happens. If I divide this one by cos squared, sine over cos is tan, so I get tan squared. That divided by cos squared gives me 1. And this divided by cos squared, that's a secant squared. So my last Pythagorean identity is tan squared theta plus 1 is equal to secant squared theta. So a trick with memorizing these is just to learn the first one, sine squared theta plus cos squared theta equals 1, and generate the other 2. Just memorize the first one and be like, oh yeah, to generate the next one I divide everything by sine squared, to generate the last one I divide everything by cos squared. It actually helps you memorize all the other reciprocal identities while you're working at it, and it certainly saves a lot of time having to actually memorize what the other 2 are worth. In the next part of this video, we'll take a look at how we can use trigonometric identities to simplify and prove trig expressions.